Creating a cinematic simulation of the August 1914 Battle of Kraśnik requires a model capable of processing high-density historical combat. However, state-of-the-art architectures like Google Flow struggle with these environments, often defaulting to severe visual hallucinations. Instead of engaging the enemy, the neural network targets adjacent friendly figures, causing allied units to turn on one another. This glitch, logged as AI-flow-fail-03, results in total API credit loss, as the model generates a chaotic, unusable mess, ignoring the historical record. Overcoming this bias involves abandoning descriptive prompts and instead engineering rigid kinematic constraints. Generating an accurate battle depends on forcing the model to ignore its internal training associations and respect fixed movement vectors instead. This map shows the borders of the German Empire, Russia, and Austria-Hungary. In August 1914, these regions became the point of origin for massive mobilization. The intersection between General Dankel's 1st Austro-Hungarian Army and General von Zalka's 4th Russian Army centered on Lublin and Kraśnik. Kraśnik was the first major engagement on the Eastern Front. It was characterized by large-scale, disciplined unit maneuvers rather than disorganized swarms. Archival accounts of deep cavalry reconnaissance, or Fernaufklärung, emphasize this discipline. Units like these maintained rigid spacing and strictly parallel lines during movement. Generative models lack an organic understanding of this early 20th century operational doctrine, often confusing disciplined formations for an internal brawl. To produce a usable result, the practitioner must provide the algorithm with a set of artificial rules that force it to respect military formations. The issue begins with how neural networks interpret visual proximity. These models lack object permanence. They have no way of calculating an off-screen enemy firing from beyond the frame. When fulfilling a combat prompt, the algorithm seeks a target. Finding nothing off-screen, it snaps its query to the nearest human mesh. In dense uniform formations, this error causes mesh merging. Tactical alignment collapses as soldiers interact with their allies. The training data typically associates high-density human clusters with riots, which reinforces this destructive behavior. Compare that to this photograph of Polish legionnaires. Modern warfare relies on a physical gap between shooter and target, a distance effectively invisible to a closed-frame AI. Because the algorithm optimizes for on-screen action, it prioritizes localized combat unless explicitly constrained. Preventing this mesh merging begins by isolating the uniform colors within the prompt logic. This log entry shows the technical solution used to stabilize the render and preserve crits. By tagging blue jackets as a fixed allied variable, we establish a constraint. These figures are prohibited from intersecting or colliding. Linking the uniform color to an immunity variable creates a logical barrier that stops the model from blending allied meshes. For high-density scenes, we must go further, implementing a log that bans all physical contact between soldiers. Forbidding actions like bayonet thrusts or sword swings removes the kinetic triggers that usually cause the model to hallucinate a brawl. Paradoxically, the only way to generate a battle is to forbid the AI from depicting any physical combat between humans. However, freezing human interaction creates a static, lifeless frame. To restore motion, we replace traditional movement with rigid, parallel vectors. These force forward momentum while explicitly blocking any lateral shifting. Maintaining these strict paths allows the model to simulate the disciplined charge of a cavalry regiment while keeping every horse and rider structurally independent. We then bring energy back to the scene by redistributing it from the soldiers into the environment. The prompt is injected with high-velocity variables, explosive artillery impacts, massive dirt displacement, and aggressive rippling of the uniform fabric. Combined with a simulated tactical camera shake, these environmental effects create a sense of kinetic impact that the frozen human figures can't provide on their own. AI motion control is most effective when it restricts the primary subjects and maximizes the physical chaos of the world around them. These methods allow us to salvage dense formations that would typically cause a total render failure. By locking the movement vectors of this Russian column, the AI is forced to respect the marching order instead of collapsing into a riot. These constraints are equally effective for high-speed scenarios, such as the massed cavalry charges common in 1914. The output remains stable even at a full gallop, keeping the cavalrymen separated and the motion fluid without any internal collisions. Rigid kinematic boundaries produce a vision of the past that is both stable and visually spectacular. Accurate historical simulation is achieved by aligning the rigid operational realities of the past with the technical constraints of diffusion models. Isolating human movement while offloading the chaos into environmental effects prevents the hallucinated fratricide that plague default combat prompts. For the practitioner, these protocols are essential tools for risk management and credit preservation. This stabilized view of the 1914 clash at Kraśnik highlights a structured tactical melee, free of modern network artifacts. Contemporary algorithms are forcing a closer look at the disciplined military structures that defined the early 20th century. Historical animation succeeds by defining the era's exact kinematic boundaries.